This video covers moment of inertia. Now, we've talked about inertia before. It comes from an object having mass. So the greater the mass, the greater its resistance to changes in motion, or inertia. Well, rotating bodies also have a tendency to resist changes in their motion, and this is called rotational inertia. Now, the way we're going to calculate it is we're going to get the sum of the mass times the distance that this mass is away from its axis of rotation, and we're going to square that distance. Now, this equation is specifically to calculate the moment of inertia of point masses. So again, the problem with this equation is it's very similar to center of mass, so don't forget to square the distance from the axis of rotation. Now remember, just like in center of mass, we're dealing with point masses to begin with. So here we have a 4-meter long bar with a negligible mass and two equal mass objects at each end of this bar. And it's rotating around a specific axis. So right now, if we know that each of these objects have the same mass, then the center of mass will be located right at the middle. So this part, example 1, asks us to calculate the moment of inertia when they are rotating around the center of their rod. So mass 1 is a distance of 2 meters away from the center of rotation, or the axis of rotation. Again, I know it's 2 meters because the entire bar is 4 meters long, and it is rotating about its center. So again, 2 meters. And the second mass is also located 2 meters away from its axis of rotation. Now, all these are going to be positive numbers because it doesn't matter the way that we are looking at this, it is still 2 meters away from your axis of rotation. So you can imagine this object as another point along its cycle, still 2 meters away from the axis of rotation. And here, I've already forgotten to put in my square. So make sure you go and include your square to your axes of rotation, or your distances from your axis of rotation. So again, when you put in all of your values, you should get a moment of inertia of 24 kilograms meters squared. Again, if you learn to recognize the units of a moment of inertia, it'll also help you remember that r should be squared. Now for this second example, it says a moment of inertia rotating at one end of the rod. So now my r has changed. Now my masses have not. So my mass is still 2 kilograms, actually 3 kilograms. And for mass 1, it is 0 meters away from its axis of rotation because it's actually rotating about m1. For the second mass, it is 3 kilograms. And now, because I know the length of the rod has not changed, it is 4 meters away from the axis of rotation. And remember to square that value. So for that one, you should get a value of 48 kilograms meters squared. So again, this is my moment of inertia rotating at one end of the rod, and for the first one we have our moment of inertia rotating about the center of the rod. For this example, we're asked to calculate the moment of inertia rotating at a point 2 meters from one end of the rod. Again, we're still looking at the same 4-meter rod, and we're still looking at the two 3-kilogram masses. So my first mass, m1, is now located 2 meters away from my axis of rotation. Remember to square that r. And we're going to add it to my mass 2, which is 3 kilograms, and it's now 6 meters away from my axis of rotation. So for this one, we should get a value 120 kilograms meters squared. What we can see from this is that the farther the axis of rotation is from the center of mass, the greater the moment of inertia. So we need an expression that will help us determine the moment of inertia when the situation arises, anytime that our axis of rotation is away from our center of mass. This equation is known as the parallel axis theorem. This theorem will allow us to calculate the moment of inertia of any rotating body around any axis, provided we know that the moment of inertia about the center of mass. So IP is going to represent the moment of inertia around any axis. The moment of inertia ICM is going to be the moment of inertia of the center of mass. M is going to be the total mass of the system. And D is going to be the distance between the two parallel axes. What that means, and we're going to see an example of that in just a second, is like in our previous example where we had our mass and rod system a distance 2 meters away from our axis of rotation. Then our distance would have been the distance from our axis of rotation to the center of mass, which in this case would have been 4 meters. So going back to the very first example, when we calculated our moment of inertia about the center of mass, we said that our distance of each object was going to be 2 meters, so our moment of inertia about the center of mass was going to be 24. So in this other example, when we're rotating about one of the masses, then our axis of rotation has moved 2 meters. So our D now becomes 2. And we get a value of 48, which is consistent to what we got earlier. For our second example, for our third example, now my axis of rotation has moved 4 meters away from the center of mass. So again, the moment of inertia about the center of mass was still 24, but now we've increased our distance to 4 meters, so we should still get a value of 120 kilograms meters squared. Now, just like in center of mass, this process can be extended to objects that are not simply point masses, but actually have a continuous mass, like disks or rods or spheres. Now, for the most part, you're going to be given the moment of inertias, and you're going to only be asked to prove that a moment of inertia is true. Now, if that's the only part you don't know in a free response, go ahead and skip it, use the moment of inertia given, and keep going. But here we can show you how to calculate it. So again, when we are dealing with continuous masses, our mass is being spread over some distance. So again, the way you want to think about an integral is that you're getting a point mass and you are multiplying by the distance it is away from its axis of rotation. But you're doing this for infinitely many tiny point masses. So for this example, which is a rod, you have a mass being continually distributed over the entire length. So we're still going to be using lambda. And remember that lambda is our linear mass density. And we said that our change in mass is going to be equal to a linear mass density times our change in position, or change in x. So in this case, because our mass is being evenly distributed over the entire length, our lambda is actually going to be equal to our total mass divided by our total length. So we can actually make that substitution now. So wherever we see dm, we're going to replace it with mass dr over L. So that means that our moment of inertia becomes the integral of r squared m over L dr. And so now if we look at this, mass is a constant in this case, L is a constant in this case, and the only thing that changes is r. And so if we're taking the integral with respect to r, we get r cubed over 3. Now, in all the situations that we deal with, we're always going to have limits for the most part. Now, you want to think about what your limits are in this case. We are rotating about our center of mass. So we want to calculate all of our moment of inertias from one end of the rod, which is negative L divided by 2, all the way to the other end of the rod, which is L divided by 2. So these are our limits. to L divided by 2. So make sure that we evaluate final minus initial minus negative L divided by 2. Here you do need to be careful with these negatives because it's being cubed. That negative is actually going to affect our values. And to make our calculations a little bit simpler, I can actually factor out that 3 from both of the fractions. So the top part here becomes L cubed. The bottom part becomes 8. The part over here becomes positive L cubed also over 8. And just to simplify this, this becomes ML cubed over 12. L. And then our last thing is to cancel out one of our L's. So that we're left with ML squared over 12. So this will always be the moment of inertia of a long continuous rod of length L. Now again, this is a really important equation to remember and be able to derive. Again, this is the moment of inertia about the center of mass of a long continuous rod of length L. So here we're looking at another long continuous rod, but it's now rotating about one of its ends. Now, you can actually use the parallel axis theorem like we saw earlier to solve for its moment of inertia, but we're going to do it using the integral just to get a little bit more practice. Again, because the mass is being evenly distributed, our change in mass is our linear mass density times our change in position. So our linear mass density is still going to be our mass divided evenly by our length times dr. So again, wherever we see dm, we're going to replace it with m over L dr. Again, very similar process. Because m and L are constants, we're going to go ahead and pull those out and take the integral of r squared. So that becomes r cubed over 3. Now, the biggest difference here is our limit. We're still going to look at the entire length of the rod, but now we're going from the length 0 to length L. So again, 0 is located at our center of our axis of rotation, and it's going away all the way to the end of the rod, L. So when I evaluate all my numbers, I get m over L. And actually, I can pull out that 3. That's L cubed minus 0 gives me ml cubed over 3l, or ml squared over 3. And again, you could have solved this using your parallel axis theorem. So again, this is the moment of inertia about one of its ends. In class, I'm actually going to give you a list of moment of inertias that you're going to be able to use. And again, on the AP exam, you're usually going to be given a moment of inertia and asked to prove it or show that this is true. And again, if you do not know how to do this, go ahead and skip it and keep going. And just a few more examples of things that you might come across. Here it says a hoop of mass m and radius r. So we're talking about a long, a very thin hoop with no mass along the inside that is rotating about an axis through the center perpendicular to the plane of the hoop. So it's really, the picture doesn't really describe it all that well. It's coming out towards the center like this. Now, if we look at our equation, I is equal to the integral of r squared dm, we can see that all of our mass is actually located the same distance away from our axis of rotation at all points. So our r is going to be equal to just capital R, because this is a constant. So if it is a constant, r squared, then we can pull it out of our equation, and our dm just becomes our total mass. Again, you can apply the same reasoning to a cylindrical shell, and this is a thin cylindrical shell, meaning you can imagine it as a bunch of little hoops all stacked together to make a cylindrical shell. Now, if you notice this, if we have an axis of rotation down the center, all of the mass is still located the same distance, r, away from our axis of rotation. So just like in our previous example, r is a constant, so we can pull it out of our equation. So when we take the integral of dm, we simply get m. So even for a cylindrical shell about a central axis, our moment of inertia is still m times r squared.